Hi everyone. My name is Ting Li.
My name is Yu Qizeng.
And I'm Kai-Xi Wang.
Today the topic of our project is to design a rapid prototype machine based on axiomatic design. Our objective is to provide rapid prototype manufacturing. And the reason for our choose this topic is that rapid prototype manufacturing is, as we know, is a key process for developing new products, whatever for company or for university lab or for some research departments. And the advantage is that it costs less manufacturing time and less material waste, and what's more, it's more flexible. And nowadays there are more than 10 RPM technologies were developed since 1986. They are these 10. And here is our decomposition. The FR0 we here is provide rapid prototype manufacturing, and according to the theme hardware component, we decomposed the functional requirements as the six parts, and we have to provide some hardware which can help us process prototype data information and support materials and input materials, then shape materials, and it also have to provide electricity for rapid prototype and provide support for rapid prototype manufacturing. And the DPs are the relative respective DPs are shown here. You can see that. This is a uncoupled matrix here.
At first, our design, we wish our design can provide the motion of the devices we used in the RPM system, and it's composed with several devices. First, we want to we want to provide the motion, so we can decompose the motion of material holder, the motion of shaping device, and the inputting device into three dimensions, the X, Y, Z dimension. But it can be seen the directions are overlap, so we reduce the X, Y direction of motion of the holder, and reduce the X and Z direction of the inputting device. We can reduce the X direction because the inputting device we wish to design it's like a linear inputting device. So and we reduce the Z direction of the motion of shaping device. And the image is our original design for the 3D printer or RPM system, and it references some existing rapid prototype manufacturing system. First, we decomposed the process prototype data information into three children: input information, convert information, and generate manufacturing paths. And the generate manufacturing paths can we decompose it to convert information. We can decompose it to transform information to STL format and eliminate the STL files. And this part normally can be done in the software, CAD software, but we wish to finish this part in our system. And we decompose the support material to material holder and vertical motion of a holder. And in this part, the provide vertical motion of a holder, we decompose it to three children. Is they are provide power, provide the path, and transform power. And And then we decompose the input material to store material powder and spray material powder and provide the horizontal motion of material inputting. The decomposition of provide horizontal motion of material inputting is similar with the provide vertical motion of holder. Is also include provide power, transform power, and provide the path of horizontal motion. Okay. At last, we decomposite the shaping material and into two children, provide the shaping device and provide the horizontal motion of the shaping device. The decomposition of provide the horizontal motion of the shaping device is similar with the previous part of the motion, provide motion. But the difference is each part of the children, the composition of the children can be decomposed into two directions and two device to and we have each child we provide one device to achieve the function parameter. And this is our final decomposition. The FR file is the provide electricity of rapid prototype. When the power is reliable, this part doesn't influence the other part. So at last, our matrix is our design is uncoupled.
This part shows our physical integrations. In the left picture, you can see the supporter frame and the material holder. The right picture shows the passes for the different components of this system. At the bottom, you can see this is a pass for the inputting devices. And at the bottom, this is a pass for the support material. And these two passes are the pass for the shaping component. And this shows some details. In the rapid prototype machine, the product is manufactured layer by layer. Every time some powder was placed onto the unfinished surface of the product, and then using laser sintering technology, we can form the powder to the product, and then after the laser sintering, the process will repeat as before and until the product is completely finished. In our design, there is an innovative idea, which is that we think the rapid prototype machine should have the capability to convert different file formats of the input information. And today, most rapid prototype machine requires a unique file format, which is mostly STL file. We think it will be convenient for the customer to directly put their design files to the machine and let the machine do the conversion for them. And thanks for your attention and questions.
You didn't give me much time to stand up there. So thanks for your attention, and then you wait for me.
I just have a question. How does this design differ from current design? What is the purpose of your design, and how is it going to help improve the 3D printing process with your access control? I mean, it seems as though that's they have those out pretty common. So it's how is yours differ from current to improve on the process?
The question is that what is the difference between our design and the technology available today? And
our design of this 3D printer, and we've integrated the software part, the data information process part in our design, and we use the linear array sprayer to instead of some current 3D printer use the linear linear array laser generator to reduce the direction of moving. So, but we use the linear superior, and we think the linear superior is cheaper than the linear laser generator. So our if we finish all the design in this part, our 3D printer may be cheaper than the others.
Any questions?
I noticed in your design matrix that you had no coupling whatsoever. I'm just kind of curious if you went through multiple iterations of coming up with DPs and FRs to get there, or
The question is, our matrix is a diagonal and uncoupled matrix, and actually, at first we saw that there is a coupling, maybe due to the power cable, and then we talked to Professor Brown. He said that most time the power is reliable, and we can ignore the influence due to the power. And for the other FRs and DPs, we actually checked, but we cannot find the coupling. Yeah.
Well, let me just say a word about power, too. Thanks. So if power is an issue, I mean, everything here takes power. So then power's coupled with everything. So what do you call it when something's coupled with everything? Constraint, right? There are some special cases where maybe you want supplementary power. Classic is like a rolling mill or extrusion or something, because if you get a power outage, all the material moving through at very high speeds, and the rolling mills has got a bunch of momentum, and if the rollers stop, it goes all over the place, and you spend weeks with a torch cutting it out. Same thing for some of the continuous casting operations. So there are some places where you might have an FR to provide backup power, but for the most part, it's like the power is reliable enough, but it's something to think about. So we seldom have an FR that's supply oxygen for the operator. Right? We assume that's going to be there.
Any other questions?
So does that mean sort of take out some of the power FRs if it's constrained? Because I did notice that there were some like provide power and transfer it to motion. Like it was 4.2 or something. Yeah, it's like provide power for motion. Like if power is a constraint, do you need that in there? Or if not, there's any except for power.
Okay, so yeah, go ahead. If you want to explain it, 4.2 point.
Yeah, 4.2.1. Yeah. Wouldn't that be coupled with 4.2.2? Because
This is the mechanical power. We use the motor to provide the.
I just remember seeing power.
Yeah.
I didn't remember that the motor was.
And the 4.2.2 is about the transformation of the mechanical power, not the electrical power. And the FR5 is about the electricity.
This might be better transmit instead of transform, right? So, so it may be just a question of sort of polishing the English a little bit, but I think it's understandable. Is it so we're transferring the power through a gear train here, and here we're transforming the power from electrical to mechanical, essentially with the motor.
So wouldn't that technically be coupled because the gear train is directly corresponds to the motor?
We use the independent gear train and motors.
In the physical integration, which we haven't discussed, and that's an interesting point that Bryce brings up. Let me just address that as a learning moment, and then I'll let you guys respond. But in the physical integration, yeah, a lot of things need to be coupled, right? And that's where we talked about the integration matrix and what things need to be next to each other. And so the physical integration is a different step than the decomposition. So both of these things are there, but are they coupled? Well, yeah, physically they need to be, because if the gear train isn't connected to the motor, nothing's turning. Right?
I think the motor is just to provide a moment of force and the gear chain to transform this to motion. So I think their function are independent, but they have to connect together. So.
Yeah, no, it's a good question, good discussion. Thanks. All right, thank you very much.